In a traditional proof-of-work network, thousands of machines compete to solve the exact same cryptographic puzzle. When one miner finds the correct random number, the block is published. The computational effort of every other machine is instantly discarded. Proof of useful work offers a structural alternative to this energy waste. Instead of searching for an arbitrary mathematical string, the network redirects its hashing power towards solving real-world combinatorial optimization problems. Clients submit tasks like training AI, routing global logistics, or processing complex scientific simulations. Transitioning consensus from arbitrary math to real-world utility requires a complete redesign of how miners select and verify their tasks. The architecture of proof of useful work relies on a dual reward structure. Miners still receive a standard block reward from the network for securing the chain. But they are also paid external bounties by clients for completing specific computational problems. This structure forces miners to make active decisions. They are no longer running identical background operations. They must actively choose which specific client tasks to pull from the network pool to maximize their income. The simulation data we are about to examine proves a counterintuitive reality. In this environment, intuitive, profit-maximizing task selection strategies fail completely. To understand the data, we have to look at the verification step. Proof of useful work replaces the random nonce with verified solutions. Miners independently select discrete problem instances from a shared client pool. They process these tasks, grouping completed solutions into a verified package. To validate the block, the system takes the hash of those combined solutions, merges it with the miner ID and block hash. If the value meets the target, the block publishes. This packaging mechanism decentralizes the workflow. Miners work at their own pace on their own tasks. An individual strategy for selecting those tasks dictates their overall network throughput. Researchers modeled this environment by simulating a network of hundreds of miners, possessing varying levels of computational power, working through a massive pool of varying tasks. They tested 3 distinct selection strategies. First, the random strategy, where miners blindly pull available tasks from the pool with uniform probability. Next, the prize strategy. Here, a rational, profit-seeking miner aggressively scans the pool and solely selects the instance offering the highest client reward. Finally, the lazy strategy. A miner evaluates their specific hardware capabilities and strictly selects the lowest difficulty task to maximize their processing speed. These 3 models pit blind parallelization against targeted, optimized behavior to see which creates a stable equilibrium. This scatterplot maps the total percentage of miner rewards across our 3 strategies. Look at this cluster of green data points pinned to the top of the chart. The simulation reveals that the random strategy captures over 98% of total network rewards. The prize strategy collapses. 1/3 of the network targets the same high-reward instance simultaneously, creating a massive computational bottleneck and widespread rejection. By contrast, random nodes smoothly distribute their effort across the entire pool. They avoid collisions and rapidly assemble block packages without contention. In a decentralized system lacking external coordination, greedy individual behavior triggers a tragedy of the commons. This random selection guarantees optimal network throughput. We can isolate the variables to ensure this data holds up under varying conditions. This bar chart measures total miner reward percentage on the y-axis against required package sizes ranging from 2 to 7 on the x-axis. The green bar remains dominant across every variation. This next graph plots the same 3 strategies across 4 quartiles of miner hardware power, starting with the fastest machines on the left. Again, the green random strategy maintains total dominance, proving that brute force hardware cannot overcome a flawed selection strategy. Within this mechanism design, strategic task selection dictates overall profitability far more than raw hardware superiority. Examining block distribution reveals a statistical paradox. The curve is heavily skewed. Roughly 30% of miners capture over 50% of published blocks. This centralization stems from hardware disparity. Faster machines publish faster. Yet total network compensation shows a distinctly flattened, equitable spread. The dual reward scheme compensates for the block inequality. Miners are paid directly by clients for solving discrete tasks, even if a competitor publishes the final block first. A proof-of-useful work network achieves proportional fairness across an unequal computational landscape, avoiding the wealth-locking prerequisites required by proof-of-stake protocols. This fixed strategy simulation has a clear limitation. The random strategy dominates only because many competitors trap themselves in the prize bottleneck. If the entire network observes this data and shifts to the random strategy, the high-value prize tasks suddenly sit uncontested. In that environment, the prize strategy immediately becomes lucrative again. The next vector of research replaces these fixed behaviors with rational agents utilizing reinforcement learning. Miners will continuously update their choices based on observable ledger signals, shifting strategies to exploit temporary network gaps. True sustainability in decentralized systems requires designing protocols that guide dynamically adapting agents toward a balanced equilibrium.